Okay, I'm going to give a proof of the general case. General of the arithmetic geometric mean inequality. Okay, so what I'm going to consider, or what I'm going to use the fact that the arithmetic geometric mean inequality holds for m a power of 2. So what that means is that 1 over m times x1 plus dot 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 plus xm is greater than or equal to the mth root of x1 multiplied all the way through to xm, where m equals 2 to the power k for some k. And we can make k as big as we like if we want. So it holds for m a power of 2, so it might hold for m equals 1024 or so forth. But I'm going to ask about what happens just x1 plus to xn over n. I'm going to ask about this, where n is strictly less than m. And of course, if I can prove it for an n less than m, where m is some power of 2, I guess you'd choose m being the next one, the next power of 2, then you're laughing. Okay, so, well, I'm going to write alpha equals x1 plus all the way through to xn over n. And what I'm going to do is I'm going to try and I'm going to add some extra variables. I'm going to consider x1 all the way through to xn, and I'm just going to add for the hell of it x plus 1, xn plus 2 all the way to xm, where m is my power of 2. So these are going to be new variables. And of course, because I'm interested, these are the real ones. I'm interested in these guys here. These are kind of dummies. Well, they're not dummy variables, but I know the arithmetic geometric mean inequality holds for any set of m variables, but I'm only interested in these guys here. So I'm just going to put some more stuff. They can be anything. They can be rubbish. I can make those what I like. What am I going to choose? Well, here is my arithmetic mean. I've got alpha equals 1 over n times sigma xi. What am I going to choose my xi's? I'm going to choose my xn plus 1 equals xn plus 2. These are all going to be the same. They're all going to be alpha. They're all going to be alpha because that makes the arithmetic mean easy to deal with. And then I'll just show you how the geometric mean links to it. Okay, so these are new variables. These are my new dummy variables. Okay, so I'm just going to start out with alpha. That's equal to x1 plus dot 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 plus xn over n. And what I want to show is that alpha is greater than or equal to x1 times all the way through to xn to the power 1 over n. I want to show this. That. So what I'm going to do is I'm going to take alpha and I'm going to muck about with it. What I want to do is to massage it into a form where I can use the arithmetic geometric mean inequality, and then I'm going to use it and see what happens. Well, that equals m over n times x1 plus through to xn over m. The reason being that I want to massage it so that this m is on the bottom, and then because that's the hallmark of a mean, an arithmetic mean of m variables, and then I'm going to apply the arithmetic geometric mean to m variables. Well, I'm just going to fool around with this. x1 plus all the way through to xn plus m minus n over n. I know it looks a bit odd. Just bear with me. xn over m equals x1 plus dot 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 plus xn plus m minus n alpha. By definition, you'll remember that alpha is the arithmetic mean of the first n variables. This is all divided by m. Equals x1 plus dot 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 plus xn plus xn plus 1 plus dot 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 plus xm, or all over n. Okay, so what I've done is I've taken these extra terms, there's m minus n terms there, and they're all equal to alpha, because all the extra x's, all these new dummy variables, were all equal to alpha. So I've just added them all up. I've just observed that the sum of them is equal to m minus n times alpha. Well, now we can do something. Now we can apply the arithmetic geometric mean inequality for m variables. So that's greater than or equal to x1 times x2 times dot 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 times xm to the power 1 over m by the arithmetic geometric mean inequality. Okay? So this is alpha. So alpha to the power m is greater than or equal to x1 times dot 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 times xn times xn plus 1 times times xm. And I've taken my power over onto the left hand side there. So these are the real ones, and these again are the dummy ones, real. I can't say real, they're the ones we're interested in. And these are the dummies. Okay, oops. So alpha to the m is greater than or equal to x1, x2, all the way through to xn, times alpha to the m minus n. Now we're getting somewhere. So that tells me that alpha to the n is greater than or equal to x1, x2, all the way through to xn, which tells me that alpha is greater than or equal to x1 multiplied all the way through to xn to the power 1 over n, which is the arithmetic geometric mean inequality. Well, yeah, there it is. I don't want to make heavy weather of this proof, but it's rather tricky. When I was putting this course together, I was looking for the nicest, slickest, cleverest proof. And this is one of 2 or 3 or 4 different proofs which you'll see around. I want to make the observation it's tricky. It's difficult. It's elementary in the technical sense of analysis. It's not an advanced proof by any means, but it's surprisingly tricky. And that tells me that the arithmetic geometric mean inequality is useful. It is a useful, clever, pleasing, nice, powerful, tight inequality. And it crops up in Olympiad questions over and over and over and over and over and over again. There it is. In fact, I'm going to write it out again. Arithmetic geometric inequality. 1 over n times the sum, I guess that's I equals 1 to n, is always greater than or equal to the nth root of x1 times xn. This is understanding that xi is strictly positive. Well, I guess you could make it equal to 0 if you really wanted to put a 0 somewhere. So there it is. And it is incredibly powerful, and I'm going to give you a whole raft of examples. Okay, I'm going to stop there.